Hi all, welcome to the first video in our second Unit 3 topic, global climate change. In this topic, we're going to be looking at three main areas. We're going to be looking at the causes of climate change, both physical and human. We're going to be looking at the impacts of climate change, and we'll separate that out by looking at the impacts on a local and global scale. And we're also going to be looking at the management of climate change, and we'll be looking at the different strategies we use to manage climate change and how effective some of these strategies are. In today's video, we're going to be spending our time looking at the causes of climate change. Now, the first thing we're going to jump into are the physical causes of climate change. Now, a rundown of the kind of stuff we're going to be looking at today. We're going to be looking at Milankovitch cycles, the impact of sunspot activity, the impact of plate tectonics, the impact of global oceanic circulation, this is very closely linked to plate tectonics, and we'll be looking at the impact of volcanism as well. Now, it's worth throwing out at this point that there are lots of other physical causes of climate change. We're talking about climate change in the very broadest of senses, so we are talking about a lot of different things that can have an impact, but we're going to focus in on these five. Now, first, Milankovitch cycles. Now, the first question really has to be here, what is a Milankovitch cycle? Now, Milankovitch cycles are cycles that look at the different ways the Earth's orbit changes over time. And we look at three main changes that the Earth's orbit can undergo. First, we look at changes to what's called precession. Sometimes this is also referred to as wobble. And we're looking at the Earth slightly changing where it sits on its axis. Now, it changes over a kind of periodicity of 23,000 years. And if we look at the diagram on the right-hand side, you can see the impact that this has. Right now, we're in a situation where during the winter, the Earth is closer to the Sun in terms of the orbit, in terms of the elliptical style of the Earth's orbit. If we move forward, 10,500 years, summer will occur when we are closer to that point in the Earth's orbit. Now, what that's going to mean is that we will have much, much more distinct seasons. So we will have much warmer summers and much colder winters. What is that doing right now? It's actually levelling out the Earth's climate a little bit. Right now, winter is not as cold as it might otherwise be because relatively the Earth is closer to the Sun. And summers are not quite as warm as they would otherwise be because relatively the Earth is further away from the Sun. Next one we look at, periodicity. Now, periodicity is this idea, it's a 100,000 year cycle, and it looks at how elliptical the Earth's orbit is. And the Earth's orbit changes in shape over this 100,000 year timescale, and it becomes more or less elliptical. And the big impact of this again is it's about how extreme seasonality is going to be. If the Earth is more elliptical, we're going to have much more pronounced seasons. We're going to have summer periods of time which are much warmer because the Earth gets closer to the Sun, and we're going to have winters which are much colder because the Earth gets further from the Sun. When the Earth's orbit is less elliptical, when it's more spherical, overall we are going to see less extreme seasons. Now, the last one we've got here is tilt. And again, we're looking at the same kind of things. This realistically affects where the thermal equator is with reference to the kind of 0 degrees latitude equator. And you can see that the more the Earth's tilted on its axis, and it's a range of around about 3 degrees, the further away the equator, the 0 degrees latitude equator, gets from the thermal equator. Now, this moves solar insolation further away from the equator and it spreads it further around the Earth. And again, this is a periodicity of around about 41,000 years. Now, next, sunspot activity. Now, the Sun gives out, huge amounts of solar insolation. We know this, or the Earth receives huge amounts of solar insolation, but the amount of energy the Sun gives out, more often than not, is fairly stable, for the next 3 billion years or something like that. It's going to be reasonably stable, but we do see changes in the amount of energy the Sun gives out, and we can correlate that to the amount of sunspots that the Sun has active at any particular time. Now, sunspot activity kind of operates in an 11-year-ish cycle where you have periods of excessive sunspot activity, and that increases the amount of solar energy that the Sun is giving out. And then you've also got minimal periods of sunspot activity where the sun is giving out lower volumes of solar energy. That means the Earth's insolation values change, and it means the Earth gets warmer or cooler on these 11-year cycles. Next, if we think about plate tectonics, the shape of the Earth in terms of the layout of the plates has changed dramatically over the Earth's history. If we have a little look at this diagram, you can see the impact that can have. If you've got large land masses near the poles, you can have large amounts of glacial ice. If you've got large amounts of glacial ice, you can have an enhanced albedo effect. That can alter the amount of solar insolation that the Earth receives, or certainly the amount that the Earth holds on to as the albedo. The enhanced albedo is going to reflect a lot more of this off. If you have not got this, if you've got continents that are more spread out, like what we have today, you have got a situation where it's harder to have extremely large ice caps. If you had a situation where the land masses of the Earth were strung out along the equator, and it's, as far as I know, it's not a configuration that we've had, but we could easily have it, then you could be very, very hard to get any major ice sheets, because obviously on top of water or sea ice, it's much harder to create than it is to create ice out of fresh water. Now, the configuration of the plates also has an impact on oceanic circulation. You know, if you look at the diagram on the right here is global oceanic circulation as we know it now. And oceanic circulation is important. It moves energy around the Earth. It moves energy from areas of surplus to areas of deficit. If we put continents in the way, that changes how oceanic circulation works, and it changes how effective the oceans can be at moving energy from the different latitudes or between the different latitudes. Now, the last one that we're going to talk about with the physical features is volcanism. Now, we tend not to make huge amounts of reference to kind of modern day volcanism having a particular impact on global level climate change. You know, yes, they certainly have an impact, but what we're really talking about are what we call areas of flood basalt eruption. Now, these are areas around the world, and you can see this map, you know, the kind of splodges of red, and forgive the kind of reasonably poor resolution of this image, but these splodges of red are huge areas where basalt has been extruded in a reasonably limited time span. You know, if we look down here, there's an area in India called the Deccan Traps. That huge area of basalt, and it is, I'll look at some images of it that show you the thickness of basalt we're talking about. It was extruded in a kind of, you know, around about a 1 million year time frame. That is nothing for the volume of basalt we're talking about being extruded. Now, coming along with that, you've got huge amounts of greenhouse gases that get extruded into the atmosphere, and they have an impact on global warming, on climate change. We're also seeing huge amounts of dust and other material being ejected into the atmosphere, and these also have an impact on how warm the Earth is or not. Now, as I say, that's going to wrap up the kind of physical causes. I have went through this really briefly. We will obviously enhance this when we talk about it in lessons, but that gives you a kind of an overview. And it's also, again, to state it again, these are not the only physical causes of global climate change, but they are some that we can use to get us started. What about human causes? Now, with this, we're going to look at 4 main causes, although admittedly fossil fuels is really broad, so there's a lot of different things that can fit in there. But yeah, we're going to be looking at fossil fuels, the role agriculture plays in climate change, the role deforestation has played, and the role that industry plays. And again, the same health warning that I talked about with the physical causes of climate change, this is not an exhaustive list. There are other causes of climate change there, and you know, we can look at those as we do a little bit of further reading on the subject. Now, first, fossil fuels. What we're looking at here is rates of consumption. And just purely to make the point, you know, as we go from the 1800s to 2016, which is where this graph ends, you can see that the amount of fossil fuel usage has increased in an absolutely incredible way. You know what I mean? And we're not terribly worried at this point what particular variety of fossil fuel we're using. The point here is that these fossil fuels are being used, they are being burnt, and that's putting greenhouse gases into the atmosphere. And some of these greenhouse gases have a bigger impact than others, but the point here is that huge amounts of them are being put into the atmosphere. If we look at this next diagram, it shows us, where are greenhouse gas emissions coming from by the different economic sectors. And we can see some of the areas that are, directly emitting greenhouse gases, and that's kind of what we're going to focus on here. Electricity and heat production, a quarter of global greenhouse gas emission. Industry in general, and we're going to talk a little bit about industry towards the end of this video, produces another 21%. Now, AFOLU is agriculture, forestry or other land uses, and that's a quarter. Buildings themselves, 6.4%. Transport, 14%. And then we've got others, which is your 9.6%. Now, we're not going to worry too much about the indirect CO2 emissions. They are obviously there as it does represent, a reasonably significant portion of the total greenhouse gas emission that we're talking about. But what we really think about is the direct greenhouse gases that are being emitted by each of these different sectors. And then we all know that these greenhouse gases, when they're emitted, if we think back to the atmosphere topic, once they're in the atmosphere, they will block some solar insulation making its way to the Earth, but they're a much more effective block of solar insulation that's trying to be re-radiated out from the Earth as long-wave radiation, and as such lead to global warming. Now, a diagram I've got up here, the parts per million of methane that we have recorded in the Earth's atmosphere, and we can see again, the trend here is with time it's increasing. Now, methane is a greenhouse gas. It is far more efficient as a greenhouse gas than carbon dioxide is. Now, the reason I've got methane in here particularly is we can track methane in to a lot of the other land uses that we're talking about. Methane production, particularly through things like agriculture, particularly livestock rearing, is something that are very, very closely linked. The human diet for beef in particular is something that grows year on year on year, and the scale of cattle ranching globally has a huge impact on methane production. And the volume of methane that we're producing is, as I say, it's a very, very efficient greenhouse gas, and that leads to huge amounts of global warming. Now, next we can have a look at this, and we're looking at some of the causes of deforestation, and we link it to other things. And this is more about linking a lot of different things together. Now, deforestation all on its own is a contributor to global climate change. Trees are carbon stores. As a tree grows, it takes carbon, it takes nutrients out of the soil, out of the air, and that then goes into the material that makes up that tree, the wood, the branches, the leaves. As if you cut that tree down, and the vast majority of them wind up getting destroyed or burned, you put that carbon back into the atmosphere very, very quickly. And then if we look at some of the reasons why we're seeing such high rates of deforestation globally, we're talking about clearing land for things like cattle ranching, for things like palm oil ranching and stuff like this. Now, this is hugely contributing to climate change as well, because cattle ranching, as we spoke about earlier, huge production of methane. All of the rest of these types of agricultures will involve huge amounts of machinery, which are going to create or produce greenhouse gases, which are going to make this a bit of a double whammy. You lose some of the impact that the trees had on taking in greenhouse gases, and you're then giving double back into the atmosphere, which drives climate change really, really quickly. Now, the last thing that I've got here is one example of industry and its impact on global climate change. Now, if we look, and again, apologies for the size of the graph, but if you look at the graph, you can get the idea that global cement production has increased vastly with time. Cement is something that we use huge amounts of, but it is a huge contributor to carbon dioxide emissions. If you look at the graph that's kind of majorly featured on the page on the right hand side, you can see that Chinese cement emissions are higher than the total carbon dioxide emissions of both Japan and Germany. Now, that is linking again into this. We are clearing land of different things that might have a positive impact in climate change. We are then using that land to emit greenhouse gases. In some places, we're using it to create cement. and that has a massive impact on climate change. Now I'm going to draw this one to a close here, guys, and until next time, I'll speak to you guys later. Bye.